Okay, hello everybody. I'm Changwoo from Igalia. Today I'm going to talk about the LAVD, update of the LAVD with my colleague Gavin. So the talk is roughly consists of two parts. The first part is that I'm going to talk about the how CPU.max feature in cgroup version 2 is implemented in the BPF side and integrate with the LAVD side. And then another major improvement of the LAVD is the load balancing. That part will be explained by the Gavin. Okay, so I believe that some are heard about the LAVD since I presented it last OSPM. But let me just quickly recap. LAVD is the latency critically aware virtual deadline scheduler, which is basically motivated by the gaming workload and initially designed for the SteamOS to run the Windows games on a Linux, the better. So one of the key heuristics that LAVD use is the waker and wake-up frequency to decide the task urgency, which is we call the latency criticality. And since it is based on the SCADAX, it is majority part of the LAVD is implemented as a BPF. And small part of this one was the implemented as a lost. And since we, after I presented LAVD in the last OSPM, we had some discussion about energy model rating. So that there was some of the improvement on that area as well. And besides that, we last year spent a good amount of time to improve the expanding the LAVD to somehow properly handle the server workload. And of course, that LAVD was not initially designed for the server workload. So we found that there are two major areas are missing. One is the CPU.max support in the cgroup version 2, and the better load balancing, a little bit more sane load balancing scheme should be properly implemented in the LAVD. So that my part is about the CPU.max support. I believe that all of you already know about what the CPU.max feature is, but in short, the concept is not complicated. Basically, system administrator can specify quarter, period, and burst for each C group. Basically, the idea is that during the period, the C group can use this amount of the CPU time, right? And the CPU time is underspanned, then up to the burst that the unused CPU time can be carried over to the next period, so that the quarter, period, and burst is the main three things user can describe in the CPU.max. So the overall flow, how the CPU bandwidth enforcement is applied in the kernel is somehow straightforward. So each C group has the quarter concept, and then the per CPU before perform the dispatch and in-queue, it actually pulls some portion of the slice from the global C group quota pool. And then if it fails to get the quota, which basically means that they already spent all the assigned budget, then the C group is going to be throttled, and the throttle task will be dequeued and parked. So that's basically the key flow. And then next time the new period starts, and then the C group will have the CPU budget, then the throttled tasks will be in queue. So that's the overall flow of how the CPU.max works. In this flow, there are three key design factors. One is that the task selection, how tasks choose a selection, thickness task should be implemented, considering the C group hierarchy. That's the one thing. And second thing is that how to detect if the C group goes beyond the quarter and was throttled. So that's the second question. And third one is how to perform the replenish of the time periodically. So let me first explain how currently these three factors are implemented in the kernel. So you have some idea in the background. So basically, in terms of task selection, the task selection is basically exploring working down the nested red black tree. For example, in this example, so that it has the two C group, and then there is a task A, and the task B and C belongs to the group C group 1, and task D belongs to the C group 2. Then it actually trees are represented nested red black tree. We should do the first red black tree lookup here in this layer, in this first level, and then go to the second level of a red black tree, which actually mirrors the cgroup hierarchy to get the task B or C, right? To get the earliest deadline. That's the key idea. But as you can see here, so the downside of this representation is that task selection cost increases linearly as the cgroup hierarchy becomes deeper. So that's the one issue. So that's the how the currently the kernel perform the task selection. And the second design factor is that the throttle detection. So currently how the kernel do is that the synchronous pool model. So basically there is a center, a C group maintains the quota, and then each CPU just borrow the 5 milliseconds of the budget to the local CPU and then consume that one. And then if there is the unused quota, then it'll actually return back to the center, the C group pool. And if the local quota is the fully consumed, it actually first try to get some more quota from its own C group. If this C group have no quota, then you actually have to traverse the C group hierarchy. So the downside of this approach is that it is expensive and also have to traverse the C group hierarchy, so which is not ideal. And the third thing is that how to refill the quota periodically. So the current implementation, if I understand correctly, requires 2 timers per C group. So basically it has the 1 timer which actually firing every period. So for the replenishing the time. And there is another timer which is called the select timer, which actually returns the unused local per CPU budget to the global per C group budget asynchronously. So the number of timers increases linearly as the number of C group grows. So that's the current status of how the C group CPU.max is implemented in the kernel. And this is our new approach. So that the design goal of the SCADX, the CPU.max implementation is somehow we wanted to improve the existing design. The first one is that we do not want it to add additional overhead in the task selection period because that's a really hot task in the scheduler. And the second design goal is that the throttling detection, that's also pretty hot task in the scheduler, so that we wanted to minimize the overhead of the scheduling throttling detection as much as possible. And the third one is that this is relatively minor, but the 2 timer per C group is too much. So if we can somehow reduce it, why not? So that's our design goal. So in order to achieve these 3 design goals, we actually come up with the 4 key ideas. The one is that let's do not use the nested red-black tree for the run queue. So how we organize the run queue, the DSQ in the SX term, is basically we have the BPF scheduler maintains its own DSQ, right? And then the task is not throttled, put the task to the DSQ, right? And the C group is throttled. Each C group maintains a separate queue, run queue, which we call the BTQ or backlog task queue. Just the throttled task is going to be placed to the BTQ. So from the task selections point of view, task selection is just a regular task selection operation. So just pick the earliest task in the red-black tree, so which does not incur any additional overhead. And that's the one thing. And the other thing is that instead of the synchronous pool model for the throttle detection, we wanted to perform the eventual bandwidth control, which means that the kernel's design is that try to be accurate and try to be immediately throttle the bandwidth within a period. But what we are trying to do is that a little bit relax the condition, so that we just enforce the bandwidth eventually, so that they control the bandwidth across the multiple period. So which basically means that a C group can slightly overspend some time, right, within a period. But if a C group make some debt, that should be paid in the next following period. So that the in the overall, we can actually still enforce the bandwidth control. So that's the one of the key idea, and actually that's the important because that actually opens the door for the off the critical path design. So our off the critical path design is that in order to make the text selection and throttle detection operations as simple as possible. So we wanted to put the heavy duty job, so like a precisely hierarchical accounting in a background task, so that the critical path becomes as cheap as possible, so that even though there is a little bit of the imprecision, that can be kind of compensated later. So that's the key idea. And then another small idea is that in cgroup CPU.max specification, the administrator can actually specify any number for the period value. So, but instead of doing that, we just normalize the period value into the standard period value, like 100 milliseconds, and normalize the quarter accordingly. So we can actually make the period of all the cgroup within the same interval. So you can that actually opens the possibility of the single timer can handle the replenish of the entire cgroup hierarchy. So that's the thing. So basically the CPU cgroup bandwidth thing for the SCADX is implemented as a BPF library, so that the kernel basically calls the SCADX hooks. For example, if the new cgroup is created, it is going to call the cgroup init, and that cgroup is terminated, it is going to call the cgroup exit. Then each individual scheduler will have their implementation of those hooks, and inside of those hooks, that it should call the library cgroup bandwidth library function. For example, cgroup is initiated, created, we should call cgroup init, or the cgroup exit should be called. And before perform the in-queue of the task to the DSQ, we should first check whether cgroup is throttled or not. So that if the cgroup is not throttled, we will in-queue to the DSQ. Otherwise, that we should in-queue the task. BPF scheduler should in-queue the task to per cgroup backlog task queue. So that's the thing. And dispatch is a little bit special, so I'm going to explain. But during the dispatch, we're gonna check that whether there is the unthrottled cgroup exists, and if there is unthrottled cgroup exists, we're gonna actually re-enqueue the throttled task to the DSQ. That should be done in the DSQ part. And in every tick, we should BPF scheduler should report how much time is spent for a cgroup. So that's basically the flow of how the kernel part and BPF scheduler part and the cgroup library part integrate and interact each other. So the key data structures, you don't need to take a look at all the details, but it's pretty simple. So that it has some cgroup context data structure. It stores the normalized quota and normalize the hierarchical quota, which considers all the restrictions of all the ancestors. And also it has the flag value, which is whether a cgroup is throttled or not. And also it has the concept of period budget. So as I mentioned, that our cgroup thing is basically pursue the eventual enforcement, so that the cgroup can actually slightly overspend, so that considering the cgroup's hierarchical quota and the unused but carry over the budget, and also the overspend budget are all the considered that actually becomes the period budget. So, and also it actually maintains the total runtimes of the cgroup CPU time used. And it also has the per LLC domain context, which basically maintains a runtime total within use consumed by the task running on that particular LLC domain. And it has the per LLC, the backlog task queue. So that's the overall structure. And quota model is as I explained, is pretty straightforward. So we actually normalize the period to the 100 millisecond, as I explained. So it has the normalized quarter, and each normalized, each C group should consider ancestors, the tightest normalized quarter to get the effective hierarchical quarter. So that is the also considered. And the C group can overspend the budget. So that is calculated as a depth. So that should be subtracted from the hierarchical effective quarter, and the C group configuration allowed to carry over some certain amount of the unused quarter that also can be added. That these three factors are considered all together, and that becomes the period budget, whether a C group can spend or during a 100 millisecond period. So yeah, so that's our quota model. And runtime accounting is pretty straightforward. So the every tick or when a task becomes the scheduled out, then the BPF scheduler should call the consume API. So basically, the BPF scheduler should report how much CPU time is consumed for a particular C group. Then the actual implementation is pretty straightforward. So you actually just look up the LLC context and just atomically add the consumed time to the runtime total per LLC. So it actually has some there is no cross LLC cache line contention across the LLC domain. So it seems to be the pretty good balance. If the LLC domain is too gigantic, and the per LLC runtime total is going to be aggregated to the C group level periodically. So that's what we call the runtime total slopey, because that the calculate time could be lag compared to the runtime total in the LLC context. And throttling is basically the two-step. The first in the critical path, that we're going to just call the bandwidth C group is throttled or not. It's just simply reading the is throttled flag variable. And if the is throttled flag variable is negative, which means that a C group is not throttled, we'll just go ahead, right? And then so this is pretty efficient because that there is no ROC, no atomics, and no C group hierarchy work, which is pretty simple. And there is another timer is running, which is accounting timer we call. The duration of the accounting timer is dynamically adjusted between the 1 millisecond to the 20 millisecond. Basically, it first traversing the C group hierarchy from the bottom up. So it actually first aggregate all the LLC, the runtime total into the C group level runtime total slopey, and it'll keep aggregating to the upper parent level of the C group hierarchy. And then if one of the C group is throttled through this process, right, the bottom up process, all its descendant should be also throttled. So that is propagated in the top-down path. And then if the task is a C group is overspend its time, so that the aggregated runtime consumed is greater than the allowed period budget, then that will become the positive, so that it should be deducted from the period budget in the next period. So that this approach, that two-step approach, is the kind of trade the detect and latency for the dispatch efficiency, but it does not sacrifice the accuracy. So we are going to present our evaluation result as well. So another thing that I wanted to do is that even though our accounting is off the critical path, but I wanted to make it as accurate as possible, so that by reducing the detectable latency. So the key idea is pretty simple. The key idea is that we just keep measuring how quickly the C group burns the CPU time, and calculate their EWMA as of their consumption rate. And periodically, we just check the remaining time and the consumption rate, and then expect that when this particular C group is going to should be throttled. And then we actually triggers the accounting timer way ahead before the cgroup is throttle. So that's the basically the key idea. So yeah, so basically the cgroup is the very rarely slowly consume the CPU time. The accounting time interval is going to be large, so it's going to have a little overhead, but it actually approaching to its limit. Then the accounting time is going to be fire more frequently, so we can actually detect the throttling moment as early as possible. And then replacement is a two-step process. One is the top-down, and the other one is the bottom-up. In the top-down process, in every 100 milliseconds, it actually traverses the cgroup hierarchy and calculate the periodic budget and update the easy throttle the flag so that the cgroup is very likely unthrottled after the period budget. And then in the bottom-up process, bottom-up part is that as a result of the top half operation of the replenish operation, it just publishes a list of the cgroup, which is the throttle. So it requires the draining of the throttle the task. And then in the bottom-up path, that each CPU, when each CPU perform the dispatch operation, it will first check whether there is the cgroup which need a BTQ draining. Then if that's the case, it will just move pop the task from the BTQ and re-enqueue the task to the normal DSQ for the execution. Yeah, so it actually design, in my experience, works pretty well because that the timer callback is pretty fast, and then the re-enqueuing, moving the task from the BTQ to the regular DSQ is done in concurrently, so that's pretty quick. So that's the key idea of the replenishment timer. So I have a few results. The first one is that we actually implemented this cgroup CPU.max library and applied to the array-VD and ran the experiment on the 2-socket 96-core AMD machine. So in total, it has 192 CPUs. And we ran the stress engine CPU operation. So in this particular experiment, we just set the quota to the 25% of the entire system capacity, and just run the stress ng -192 and just see that how the EVDF, the in-kernel version, and array-VD can precisely control enforce the CPU utilization. As you can see, red line is the EVDF result and the blue line is the array-VD result. They are more or less the same. So in this experiment. And another experiment is that the overhead. So, but measuring the scheduler overhead is pretty tricky. I don't know that whether the other people actually measure the scheduler overhead, but for this particular purpose, how I do is that just run the stress ng that CPU on the user space. So basically, the stress ng that CPU is the purely compute heavy, right? So it does not cause system calls, so that the user space time is purely the stress engine, so that in other words, the kernel space operation is only scheduled very likely 99% of 9 the schedule operation. So basically, we just run this ng the CPU and run the perf stat and measure the CPU clock cycles consumed in the CPU's kernel time and the entire time, and calculate the overhead, schedule overhead, including everything. So that's the thing, and and we actually run the evaluations on the 2-socket, the same AMD machine, and this is the result. In this graph on the left-hand side, we set the load to the 100, that basically means that the cgroup quota is the 192 CPU, and we just run stress ng with 192 thread. That's the basic load, meaning of the load 100%, and change the cgroup depth from the 1A1632 and measure the overhead in terms of the clock cycle spent in the kernel time and the entire clock cycle. And then they convert that number into the number of CPUs, so for the ease of the understanding. So when the cgroup depth is the low, the LAVD and EVDF has a similar level of the overhead, but the cgroup hierarchy becomes the deeper. EVDF overhead increases as expected, but the LAVD overhead is still remain similar. And the graph on the right-hand side is we set the cgroup depth to the 32 and change the load. The 100, as I can say, as I said, means that the stress engine is CPU 192, and in case of 200, 192 multiplied by 2, right? So that the how the overhead changes, the LAVD more or less the same, and if the load is below the 100, then LAVD overhead slightly becomes the lower, but not a lot. But the EVDF, the overhead becomes larger because you should access to the global, cgroup pool to get the more budget and perform the throttling operation in the critical path. So in summary, we actually use the LAVD CPU.max library as a O1, and task selection is the doesn't have additional overhead, and the throttle detection is the asynchronous and off the critical path, but the long run accuracy is exact. Yeah, that's the summary of the CPU.max part. Any question until this? Before moving on to the next part, Andre?
Yeah. So the backlog queue, the BTQ, it's currently based on ATQ, right? So that means I need to use PPF arenas, which sometimes is, I mean, if we move forward with kernels and tool chains and whatnot, it's not going to be a problem. But if I need to use this like in a older kernel, older distro, it might be problematic. And is there any way to implement the same BTQ machinery in using the SQs?
I think that should be possible. One of the main reasons that I choose the ATQ, which is the arena-based redirectory implementation over our own DSQ, is because the DSQ do not have the API moving a task from the one DSQ to the another DSQ. The only way to move the task is that the moving a BPF scheduler DSQ to the local DSQ for the execution, kind of that. So we
have iterators, right? So in theory, you could use these iterators to move across two DSQs.
Yeah, that will be possible, but that is a bit expensive. So that's why I actually choose the ATQ. And if we have just a direct to task transfer from the one DSQ to the another DSQ, so we can actually replace the ATQ to the DSQ. So
maybe that's something we can add. Like
yeah, sure.
To move one single task.
Any other question?
Maybe a naive one. Any interest or chance to contribute any of those completely fancy set of features to the in-kernel implementation? Because I mean, you are essentially rewriting completely something that is there. Maybe you could have made it better.
Yeah, so that's something that I like to discuss with the community. So because that from my point of view, the first one is that whether this idea will really work as designed, and after months of the effort, it confirms that the design seems to be reasonably manageable and overhead performance numbers are as expected. But if there is someone who are interested in this direction and improving the CPU.max, in-kernel CPU.max implementation, yeah, welcome to collaborate.
I have one question before that. Did you run your tests and your comparisons after the throttle rework? Because it has changed quite a lot. Yeah, like since end of last year, throttle stuff is quite different. Like we don't, for instance, the throttling actually happens when the task is about to return to user space. So we don't do it immediately in the kernel. So for instance, the thing with you can have a depth carryover. Like if you, for some reason, have to spend a lot of time in the kernel and cross many periods, you're going to do that. But then you're going to stay throttled for a while to like pay this back. So we sort of have this now, but I don't know if that's what you base your stuff on or not.
Yeah, I think that there's similar ideas that we actually use. can be somehow applied to improve the existing implementation.
But which kernel version did you use?
I think that this is the pretty recent version. It is not 7.0, but the pretty recent version.
And when it was merged, the latest?
I think it was like September of last year. So
When it was more?
So it's just that there was some large rework of the throttling mechanism.
Yeah, that's what I was told. That.
And okay, so your comparison include this change?
I don't think so.
Okay.
Yeah. So yeah, of course that thing is the landed that the overhead of the EVD, the in-kernel version of the CPU.max implementation will be lower, becomes lower. Yeah.
it should be 680.
618.
For CPU or
Which one?
the backlog queue
That's a per LLC domain.
per element.
Yeah, per LLC domain.
I have more than a question actually. Have anybody tried to look at this group model, the best way to fix the problems, whatever problems trying to fix? Can we do better by actually implementing something simpler?
Can it do it better in the kernel side or the BPF side?
I mean, we're trying to control some kind of bandwidth control for the group level. I mean, is the current implementation because you're trying to improve some kind of implementation details? But like, can we actually create a different model to achieve the same results without having this hierarchy and all these calculations? I know that Peter had some flat hierarchy stuff, and I am generally in the opinion it's better to operate at one flat hierarchy and just get rid of all these stuff. But I'm not sure what's the problem that really must be fixed by this hierarchy.
The whole interface is hierarchical. So you have to do some hierarchical accounting in order to constrain the interface.
Yeah, that's true.
But yeah, I mean,
So
is the control has to be hierarchical as well. I mean, do you really need to describe it?
That's how it is. That's how cgroups are defined.
Also in your
I think that's the problem.
the C group hierarchy work actually happens only in the background accounting time.
Yeah, correct. But you walk the entire hierarchy.
Yes.
And you see if anything has crossed the whatever was the remaining budget, and then you decide to throttle from then on below.
Yes. Just faithfully following the C group specification.
Sorry, I missed it, but that carryover, does that mean if I only run every other C group going wake up like every other?
So here you will even walk the hierarchy even if nothing is throttled, because you have to go and find out whether something is overrun or not.
Do I still pay the debt if I don't run for one entire period? Like
Suppose that the C group do not run at all, right? And the administrator do not specify the burst, the amount of time that can carry over, unused time carry over to the next period, then you're done. So you're gonna just have the starting from the fresh restart value. But suppose that the administrator said, oh, you can carry over the unused time until the 20 millisecond, then up to the 20 millisecond of the burst time can be carried over, unused time can be carried over, but the C group is somehow overspent like 10 millisecond, then 10 millisecond is going to be deducted. So plus 20 minus 10, so we're gonna have the 10 additional budget. Yeah. Okay, so I think if there is no question, then Gavin is going to take care of the improvement in the load balancing side.
So, okay, so Changwoo has finished the CPU.max implementation side. So I'm going to introduce like the new load balance, maybe the mechanism or policy in the LAVD. So, and yeah, and LAVD is a domain DSQ scheduler, which means that each domain has its own DSQ, the dispatch queue, and all of the CPU under the domain share the same DSQ. And the domain DSQ has two rules in general. The first rule is the stealer. Stealer is the underloaded domains which periodically pull tasks from the stealing. to keep its CPU busy. And still is the overloaded domain, and which have like more QE load, and we need to periodically try to take the task away from the stealthy. And how the load balance happen is that when the CPU local run queue is joined, and then OPS dispatch will be called, and inside the LVD, the first thing to do is that if it's the stealer will try to steal the task from the stealthy, which is a load balancing. And the second one is that if it's a normal queue, it will just take the task from its the domain DSQ. And if finally there is still bubbles happens, we will try to force steal from any nearby DSQ. And okay, so let's talk about the current limitation of the LAPD load balancer. The current loading metric is the CPU utilization and plus the scale QE length. Yeah, and not the text size. So it's obviously, this is the problematic like low metrics. And the second one is that when we try to migrate like the task from the stealthy, currently we don't have the specific design, the budget. And we just steal one at a time and have this kind of probabilistic control to drop earlier to avoid this kind of thundering herd problem. And the third problem is that when we try to migrate a task, it's always try to take the task from the QE head. And we don't have the specific preference, which kind of task we should migrate it from the stealthy to the stealer. And this chart is the visualization. What is the current load balancer design? There are three rows. The first one is a stealer. Stealer is the domain QE load is lower than the average the domain load minus the delta. But what is the average one? Please take a look at the center, like horizontal line. The center one is the average QE load across all of the domains. And we will try to calculate like the delta. And the delta is adjusted according to the current system loading. And stealer is the domain lower than the average one minus the delta. So in this chart, we can see like the green color, which is the stealer, is the domain 2 and domain 7. And for the stealthy is the loading above like the average plus like the delta. So in this chart, there are two, is the domain 1 and domain 6, and the color is the pink. And all of the others, which is located in the central band, is the blue one, and is a normal domain. And this rule category will be a profile, and every 10 milliseconds to assign the rows. Okay, so how we design the new QE load metric is by, we replace like the task queue length with the task queue size. Yeah, and you can see like the new equation is the domain load equal to QE load plus like the utilization. And the QE load is a summation of the all task, the task size in the system. Yeah, so this is the total QE load. And the other one is the utilization. Utilization is an invariant utilization of the CPU loading inside the domain. And after we determine like the QE load, but how can we determine which QE load a specific domain should carry? We use this kind of like a fair share mechanism concept. It depends on the domain capacity. Okay, yeah. For example, if we have the heterogeneous system and then we have the performance domain about 40% of the capacity, we should carry like the total QE load 40% to this specific domain. That's the design idea. So I think this chart it's very good demonstrate like the idea. For example, if the total QE load is around like 10,000 and the performance domain is around like 40% of the total capacity, then it should carry like 4,000. Yeah, the QE load. So after we determine like the QE load for each domain should carry, we need to decide what's the budget when migration happens. And the budget design is like 50% of the excessive like load beyond like fair share and the QE load. Yeah, for example, if see the right side, we have the steely and stealer. And for the steely has the more QE load than the fair share. So we have the gap. And we take the gap out like 50%, and 50% is the amount to be migrated out if the load balance happens. And for the stealer is similar, is symmetric idea. If we have like 50% like a deficit load, and then we only take like we have the gap, and then we only take like 50% of the load from the steely.
You have a question?
So just to follow your presentation, can you go back one slide?
Okay, sure.
Just to follow. So you estimate the capacity for the big domain, and then I realize this is not ARM big B2 system, it's a SMT system. You estimate the capacity.
Yeah, this is similar to Ricardo's representation yesterday, because I use the S1 Carbon. So there's a Meteor Lake architecture. So go ahead.
And then you always estimate this capacity that way, that they are like independent for CPUs in this SMT system. Is this SMT system there?
This is heterogeneous system. Like there are four cores in the performance domain, and like
hyper-threading?
yeah,
There is.
I think so.
Yeah, yeah. Hyper-threading is also a consideration, but currently our implementation is just consider like
okay, assumes that
right.
This is independent core with
right
4 times 1,000 and 4,000.
Okay. Right. I think it's similar to the last yesterday the architecture. My architecture is around like four core in the performance domain and 8 core in the medium domain, E core. And the last one is low power domains, like 2.
I think that you have 2 cores in the performance domain.
Yeah.
Which is for CPU total, and the rest is as you said.
Yeah.
Is it fair to assume that they are kind of same capacity and independent?
Absolutely not.
Yeah, sure. SMT will impact to each other, of course.
Okay.
Yeah, but it's just because it's just the current implementation. We can consider that and try to enhance in the future.
But then you try to load balance, and if you estimate this capacity.
Right, of course. Yeah. It's a valid concern.
Okay.
Yeah.
Thank you.
And I also, that's also the discussion I wanted to have in this presentation, because I want to hear more about experience in like especially like Intel or maybe ARM, and how can I improve this in the future? Because currently I just implement it by the very heuristic mathematical way, but it's not considered like a low level, like different, not only maybe SMT. I don't know if there is any other considerations I need to consider in the future. Yeah. Okay, so this one is the evaluation, very easy evaluation test, because currently we are focusing on the wake up latency. So I only put this chart here, and I want to talk about like they are interesting number. For example, like P99 on the left side, this is a material lack CPU architecture. So, but for P99, the 4.3 is compared to LAVD, normal LAVD without the implementation. So it's around like 4.3%. improve. But if we compare to the homogeneous system, it's in the AMD EPYC, 192 CPUs, it's a 2-NUMA machine. The improvement is around like only 2.1%. So I think this kind of capacity aware like balance work better on the heterogeneous system, the improvement. And for the P99.9, yeah, it's consistently has like 7.1% of improvement compared to the LAVD normal.
Meteor Lake is also one with SMT on the P cores, right?
No, on the P cores.
Yeah, but on the P cores there is SMT.
Mm-hmm.
Yeah.
Okay, so yeah, that's the future work. As I mentioned, I also want to open the discussions here. Okay, so even if we have this kind of task size migration, as I mentioned, that currently we only migrate like the head of the DSQ, the task from the head of the DSQ, and yeah, it's of course it's not the best candidate to migrate, and so we also want to implement this kind of selective migration, and yeah, and to prefer what's task to be migrated, maybe we need to have a prefetch and try to pick into the next 2 to 8 because this is a domain DSQ. So maybe we can try to have some kind of pick into the future to select like the possible task to be migrated. And on the other side, we also want to consider which kind of task we should not migrate. It's, for example, like task hard, yeah. So it has been maybe running just in the last 500 microseconds. Yeah. So, yeah, so I think this is just open discussions. Maybe, as you mentioned, maybe SMT could be the problems, or do you guys any see other problems, or anything can be improved, or
So you go back to the SMT part.
yeah. Which one?
How are you determining that the capacity is 4,000? 4 logical processors.
We saw the
2 physical cores.
sister devices, CCFS, try to capture like the number of the topology from the booting. Yeah.
But I mean, if you have an SMT core,
Right. But
what one sibling is doing is affected by what the other is doing or not.
right.
So if one sibling is idle, you have 100% capacity.
Right.
But as soon as the sibling start doing some work, you have reduced capacity, and you will also have dependency on the workload because it may be that one is doing computing intensive work while the other one is doing memory-bound work. So you will have capacity, more capacity in that case, but both are computing intensive. So capacity estimation is not very.
But can we? How can we observe this kind of situation? For example, if we have the 2 core, they are share the same physical core, they are SMT. When we are running on top of the one SMT core, and then this SMT hyperthreading maybe have 80% of CPU utilization. But how can I know like the impact between these 2 SMT if there is any efficient way, and then I can decrease another CPU capacity, and that's what impact like the load balance decisions in the future, right?
Yeah.
Right, but I don't know if there is any hardware index, or how can I maybe just try to use like a networking approach. I can try to profile, try to feed more tasks to see, or anything. I don't know. It's just some kind of.
So in the mainline kernel, down to, for example, EAS on SMT system.
Even if you could track capacity, you will going in and out of idle so fast that it will be very difficult for you to track the capacity without incurring a big overhead. But you will essentially need to be tracking the idle state of the CPU.
Yeah, basically we don't use capacity. So systems.
Okay, so but what's the metrics you are using with
So the scheduling is done by priority,
okay.
which means that, you know, the priority depends on the capacity, but or is proportional to the capacity, but the SMT siblings have the lowest priority. So they will be populated last in this. So actually, on Meteor Lake, we won't even run CAS
Okay.
as a. Unless you disable SMT, in which case it's fine, because then.
Yeah, but disable that is not acceptable for user. Yeah.
Yeah, it's only priority with this CPU
Right.
more important than this other, and that is how the decision is made. Yeah, so how you say SMT is used last. It depends on whether one of the siblings is busy or not, because we don't use capacity at all for systems like that.
Okay.
It's impossible to track.
Right.
So particularly usually I think the equal like capacity like, or something, remember correctly. So actually like oftentimes the little CPU will be even more capacity than
And we call with a busy siblings. Yes. Yeah.
Time's up. Okay. Okay. Thank you.
Thank you.
Thank you.